It is 2 in the morning. Your coffee went cold hours ago. The rest of the house is dead quiet. And I mean, the only light in the room is the glow of your IDE reflecting off your glasses.
Yeah, just burning the midnight oil.
Exactly. You are debugging some stubborn API call, just trying to keep your head above water while it feels like the entire tech stack of the world is being rewritten overnight.
It really does feel like that. Like,
It does. And while you've been working on that one script, an AI just watched a video, read a textbook, and wrote a better function than both of us combined.
which is simultaneously amazing and terrifying.
Right. So tonight we are talking about exactly how it did that. If you are that software engineer out there right now, just trying to parse the dizzying reality of modern AI, this deep dive is for you.
And honestly, the ground is shifting under our feet at an unbelievable rate. I mean, the gap between what we thought was possible a year ago and what is running in production today.
It's massive.
It's entirely due to the leap we're discussing tonight.
Right. Which brings us to our stack of notes for this session. We are pulling from episode 132 of the LLM Mastery Notes, and they're focusing squarely on the world of multimodal models.
The ability for an AI to see and hear.
Exactly. The core mission here is understanding what happens when we stop treating AI like a text-in, text-out terminal and start giving it eyes and ears. Because as engineers, we spent the last decade mastering text.
Yeah, we got really good at parsing strings.
Right. We figured out tokenizer algorithms, built transformers, but the physical world isn't a text file. It's noisy, it's messy, it's visual.
We're moving from parsing strings to parsing reality.
Mm-hmm.
And that requires a complete architectural paradigm shift.
It's not just a minor pass.
No, it's not a software update where you just bump a model from version 3 to version 4. To make a machine actually see and hear alongside reading, we have to fundamentally rethink how sensory information is represented mathematically.
Okay, so before we can build a system that understands the whole messy, real world, we have to look at the individual components that capture it, right?
The individual senses.
Yeah. According to the notes, multimodal models achieve this by combining specialized sensory encoders with a powerful language model backbone. So specifically, the industry relies on architectures like VIT.
Vision transformer.
Right, vision transformers for image processing and Whisper for audio.
Exactly. So the language model backbone is, think of it like your central processing unit. It's a phenomenal reasoning engine.
But it only speaks text natively.
Right. An LLM natively only understands discrete tokens, basically just integer representations of word chunks.
Yeah.
If you feed a raw, dense matrix of RGB pixel values or a continuous audio waveform into a standard text LLM,
It throws an error, I assume.
it absolutely throws an error. It has no idea what to compute. The data is entirely out of distribution.
Okay, let me put this in system architecture terms for a second. Is this basically a microservices architecture for an AI's brain?
How do you mean?
Like, you have VT running as an independent worker service handling the pixel arrays, Whisper running as another service parsing the audio frequencies, and they just, I don't know, pass their JSON payloads down to the monolithic LLM backbone to figure it out?
Well, it's actually a bit more integrated than that.
Oh, really?
Yeah, it's less like independent microservices passing JSON over a network and more like compiling completely different high-level languages down into the exact same machine code.
So a single CPU can execute them seamlessly.
Exactly. The LLM doesn't want JSON. It wants embeddings.
Embeddings being those giant arrays of floating point numbers that represent concepts.
Correct. The specialized encoders are essentially heavy-duty compilers. So a vision transformer takes an image, slices it up into a grid of 16 by 16 pixel patches, and linearly projects those patches into vectors.
So it's translating spatial relationships like edges and colors into math.
Right into a mathematical format. And Whisper does the exact same thing with the sequential, time-based frequencies of human speech.
Got it. The monolithic LLM needs these compilers because it can only reason over a continuous vector space.
Precisely.
But wait, if we have these separate compilers turning images and audio into vectors, and the LLM turning text into vectors, how do they ensure they are speaking the same mathematical language?
That is the million-dollar question.
Like, if VIT outputs a vector for a picture of a cat, how does the LLM know that vector corresponds to the text token for the word cat? The source material points to something called CLIP as the translation protocol.
Yes, CLIP is the critical bridge. It stands for Contrastive Language Image Pre-training.
Developed by OpenAI, right?
Yep. And it is arguably one of the most elegant mathematical breakthroughs in this whole space. CLIP uses a contrastive learning approach to align images and text into a shared embedding space.
A shared space, okay.
Yeah, that single technique unlocked almost everything we see today in multimodal AI, from, zero-shot classification to semantic search.
Wait, hold on. Contrastive learning. Does that mean the AI is literally contrasting pixels against letters? Because mathematically, that just sounds impossible.
Right, it sounds like apples and oranges.
Yeah. How do you compare a JPEG matrix to a text string? You can't subtract a string from an RGB array.
You don't. And that's the genius of it. You map them both into a third shared mathematical dimension.
Oh, I see.
Imagine a massive high-dimensional coordinate system. Let's say 512 dimensions.
Okay, my brain hurts already, but go on.
Right, so you pass the image through a vision encoder to get a point in that 512-dimensional space.
Right.
Then you pass the text caption through a text encoder to get another point in that exact same space.
Oh, and then you just measure the distance between the 2 points.
Precisely. You calculate the cosine similarity between the image vector and the text vector.
That makes so much sense.
During training, CLIP takes a batch of thousands of image-text pairs. The objective function is brutally simple, honestly. Maximize the similarity between the correct pairs and minimize the similarity between all the incorrect pairs in that batch.
Okay, so it's forcing the model to play a massive, high-speed game of match or no match.
Exactly.
It just keeps adjusting the weights in the neural network until the text vector for golden retriever and the image vector for a photo of a golden retriever land at the exact same coordinates.
Yep. Over hundreds of millions of iterations, that shared embedding space just organizes itself beautifully. Concepts cluster together regardless of their medium.
So the text fluffy dog, the audio of a bark, and the pixels of a golden retriever all map to the exact same neighborhood.
In that high-dimensional space, yes.
Okay, so what does that shared space actually unlock for, a software engineer trying to build an application tonight? The notes mention zero-shot classification.
Well, historically, if you wanted an AI to recognize a hot dog, you had to explicitly train a convolutional neural network on, say, 10,000 pictures of hot dogs.
And 10,000 pictures of things that are not hot dogs.
Right. That's explicit supervised learning. It's incredibly expensive and really rigid.
Because if you suddenly needed the model to recognize a hamburger, you had to start the training process all over again.
Exactly. You're starting from scratch.
Yeah.
But with CLIP's shared space, you get zero-shot capabilities. The model doesn't need to be explicitly trained on a brand new classification task.
How does that work in practice?
If you hand it an image of a novel object, the vision encoder just maps that image to its coordinates in the embedding space. Then you simply pass it a list of text labels, so hot dog, hamburger, pizza.
And you just see which text vector is floating closest to the image vector?
Exactly. It classifies the image automatically without ever being explicitly trained on that specific categorization.
So it isn't learning what a hot dog looks like. It's learning where the abstract concept of a hot dog lives in the universe of all human concepts.
Yes.
That is wild.
It's a profound shift in how machines understand data.
But wait, if CLIP perfectly aligns these concepts into a shared space, why can't we just plug CLIP into a massive text model like GPT-4 and call it a day? Like, why is Google spending billions of dollars and consuming entire power grids to rebuild Gemini from scratch if the translation protocol already exists?
Well, that tension right there is the defining architectural debate in the industry right now. We are looking at two radically different engineering philosophies.
Okay, let's get into it.
It's the adapter approach versus the native approach.
Let's break those down. On one side, the adapter approach is what powers models like GPT-4V and Claude 3, right? The philosophy is to take an incredibly powerful, already pre-trained language model and just bolt the vision capabilities onto it.
Right. Think about the economics of a frontier model. Training a 1.8 trillion parameter text model costs tens of millions of dollars in compute.
It takes up thousands of H100 GPUs for months.
Exactly. You absolutely do not want to risk degrading that model's reasoning capabilities by retraining it. So you freeze the weights of the LLM.
And you freeze the weights of the vision encoder, too.
Yes.
But if both the LLM and the vision encoder are frozen, how do you bolt them together? They can't learn how to talk to each other.
You introduce a small, trainable neural network right between them. This is the adapter, often called a projection layer.
Oh, okay.
It acts as a bottleneck. It takes the visual embeddings from the VIT and mathematically projects them into the exact dimensional shape of the text tokens that the LLM already expects.
And you only train that tiny bridge.
Exactly. It saves massive amounts of compute and gets you to market incredibly fast.
I can picture our dev listener thinking about this like refactoring legacy code. The adapter approach is like taking a reliable, ultra-fast gas-powered car, ripping out the trunk, and just bolting an electric motor to the rear axle.
Yeah, that's a great way to look at it.
You get a hybrid vehicle. I mean, it works, it's efficient to build, but a bolted-on engine is never going to run as seamlessly as a vehicle designed to be electric from the chassis up.
Which brings us to the core argument for native multimodality.
Right, like Google's Gemini architecture.
Yes. Instead of training text first,
Mhm.
freezing it, and then projecting vision into it later, native models are trained jointly from Epoch Zero.
How does that actually work at the data pipeline level?
They use interleaved data, so the training context window isn't just a block of text. It's a sequence that might contain, a paragraph of text, followed by an image, followed by more text, followed by an audio clip,
All mashed together.
all in one sequence. The neural network's weights are updating and learning the relationships across all those modalities simultaneously.
Okay, but for the developer listening who wants to actually build an application on top of these models, how does this native versus adapter debate impact their day-to-day, like API latency, cost, output quality?
Well, the native approach is a much harder engineering challenge because the loss functions are incredibly complex to balance. But the ceiling for comprehension is theoretically much higher.
Because it's not bottlenecked.
Exactly.
Mm.
A native model doesn't have to force visual concepts through a tiny lossy projection layer just to translate them into text tokens. The conceptual representations are woven together intrinsically.
So it actually understands the physical world more deeply.
Right, which translates to fewer errors in complex spatial reasoning tasks, like asking the AI to analyze a highly detailed architectural diagram or a dense software architecture chart.
So it's the difference between learning a foreign language fluently as a toddler versus using a really fast translation dictionary as an adult.
That's spot on. The toddler has a holistic understanding of the concepts. The adult is always translating back to their native tongue first.
But, even with these massive architectural investments, combining these senses introduces entirely new, frankly, terrifying bugs into the system.
Yes, it really does.
The source notes highlight a critical flaw that plagues both adapter and native models: multimodal hallucination.
Yeah, hallucinations in text-only models are something every engineer has dealt with. The model just confidently outputs a Python library that literally doesn't exist.
We've all been there.
Right. But multimodal hallucination is a fundamentally different beast. This occurs when the model's language generation becomes completely detached from its actual real-time visual perception.
Let's get specific so we can visualize this. You show the AI an image of an empty table. You prompt it. Describe the object next to the coffee cup on this table.
Okay.
The VIT processes the pixels. It clearly sees an empty table. It sends that vector to the LLM, but the LLM replies, "There is a silver laptop next to the coffee cup."
Yep.
Why doesn't the vision data just override the text prediction? Why does the LLM completely ignore its own eyes?
To understand that, we have to look at the fundamental loss function of the LLM backbone itself. At its core, an autoregressive language model is heavily optimized to predict the next token based on statistical probabilities.
Right. It's basically autocomplete on steroids.
Exactly. It has been trained on trillions of words from the internet.
Okay.
And in that massive training corpus, the prior probabilities of the phrase coffee cup being spatially adjacent to the word laptop are astronomically high.
Oh, wow. So the prior probabilities learned from all that text training actually overwhelm the real-time continuous vectors coming from the vision layer.
Yes, exactly. The neural network has attention heads deciding how much weight to give the incoming visual vector versus its own internal language priors.
And the priors win.
Often, yes. If the internal statistical bias is strong enough, the language backbone just steamrolls the vision encoder. The weight of the text training just bullies the visual data into submission.
So it confidently describes a laptop that isn't there because the statistical math says a laptop should be there.
Right.
It's like the AI is saying, I don't care what the pixel array says. My weights say coffee cups sit next to laptops, so I'm generating the laptop token.
Pretty much.
That is fascinating and also slightly terrifying for anyone trying to build an autonomous agent using these vision APIs.
It's one of the hardest unresolved challenges in alignment right now. The language model is just too aggressive.
Well, this begs the question then. If building these systems requires massive H100 clusters, sparks endless architectural debates about projection layers, and introduces stubborn bugs where the AI hallucinates objects based on text bias, why are we doing this?
Good question.
Like, why is every major lab pivoting away from pure text models?
The short answer is deployment efficiency and cognitive scaling. For the developer writing code at 2 a.m., true multimodality is an absolute infrastructure dream.
Yeah. Think about the current microservice hell of building a complex AI feature. If you want an app that takes a user's voice note, transcribes it, looks at a photo they uploaded of a broken server, and writes a diagnostic summary, you are chaining APIs for days.
Oh, totally. You hit the Whisper endpoint for audio, you wait. You
Right.
hit a ResNet or VIT endpoint for image tagging, you wait.
You take those strings, inject them into a massive prompt template, and then hit the LLM endpoint for the summary.
Right. You are dealing with latency on top of latency. You have multiple points of failure, redundant network calls, and massive context loss because the image features are being flattened into crude text strings before the LLM ever even sees them.
But with a true multimodal endpoint, you just package the raw audio binary, the raw image binary, and the text prompt into a single payload. You make one API call.
Exactly. The model processes the interleaved data natively and streams back the summary. The latency reduction is massive.
So it's an op stream.
It really is.
Yeah.
But beyond infrastructure, there is a profound cognitive benefit here. Cross-domain knowledge transfer.
How so?
By sharing a high-dimensional embedding space, the model actually transfers understanding across modalities. For example, if a model understands the physics of how a guitar string vibrates because it was trained on thousands of video frames.
That visual understanding mathematically guides and improves its ability to process the audio waveform of the guitar.
Exactly. The modalities act as constraints and guides for one another.
The visual data grounds the audio data, and the text data grounds them both. It is inching closer to the interconnected, holistic way the human brain processes reality.
It's really the only viable path forward to artificial general intelligence. Text alone simply does not contain enough bandwidth to describe the physical laws of the universe.
Man, looking at the clock, I know we need to let our listeners get back to their terminals. But the notes for episode 132 ended with a teaser for what they're covering next week.
Oh, right, episode 140.
Yeah, they are diving into video generation. We are talking about models like Sora that extend everything we just discussed tonight into the temporal dimension.
Yeah, moving from static embedding spaces to temporal consistency is an exponential leap in complexity.
I can only imagine.
Maintaining object permanence frame by frame while generating accurate physics. It pushes the absolute boundaries of current hardware.
We will absolutely be doing a deep dive on those notes when they drop. But to close us out tonight, I want to leave you with a philosophical puzzle to chew on while your code is compiling.
Yeah, we spent a lot of time analyzing multimodal hallucinations, right? How the AI's language priors overpower its visual sensors because of strong internal biases.
Right.
But if the ultimate goal of multimodal AI is to perfectly mirror human cognition by integrating the senses, aren't they already mirroring us perfectly with these exact flaws?
Wait, like human cognitive biases, optical illusions, the Mandela effect?
They happen for the exact same mechanical reason. Our human brains override our optic nerves constantly based on our prior probabilities. It's what we statistically expect to see in a given environment. We hallucinate continuity all the time.
Wow.
So if engineers successfully patch this bug, if we force the AI to perfectly and coldly report only objective visual truth without any biased reasoning overriding it, do we actually make the AI less human?
Okay, that is going to keep me staring at the ceiling tonight. To everyone out there listening, keep tinkering, keep pushing the boundaries of the stack, and stay curious. We will catch you on the next deep dive.